If you grew up in the East Coast and are of a certain age, you might remember a company called Sinclair Oil. I actually think they still exist in Indiana or something like that. I am of that age, and I grew up on the East Coast, and Sinclair Oil always had this dinosaur as its logo, and in fact, they got to a point where they used to get these big papier-mâché dinosaurs and drag them around the country on trailers. And so I grew up believing that oil came from dead, rotten dinosaur guts. Then a lot of other things happened, and eventually I got to be a geologist or geophysicist, and I learned that that wasn't true. I also put this slide up because there was a time when it was $1.09 a gallon for unleaded gasoline. Anyhow, so how do you make oil? Oil, in fact, doesn't come from dinosaurs. It comes from small marine organisms that live in the sea, microorganisms, foraminifera and coccolithophores and things like that. These little tiny microscopic organisms float around in the ocean, and when they die, they fall to the bottom, and their bodies or their organic material gets incorporated into what's called a source rock. Generally, it's a mud or something like some kind of fairly fine-grained material. Eventually, those bodies decay, so it's dead, rotten microorganisms that produce oil, and that oil forms in that source rock. But if it just stays in the source rock, it doesn't actually produce anything that's economically useful or that's economically accessible. And so what you need is that on top of the source rock, you need something else to be deposited where these little tiny microscopic droplets of oil or organic material can slowly migrate and collect. So you need something that's fairly porous. So typically a reservoir rock would be something like a sand, or in some cases it's a carbonate coral reef. But there are different kinds of formations that allow this material to migrate and then collect. But that's not enough, because if it just migrated into the reservoir, it would then migrate up through the reservoir and escape. So on top of that, you need another kind of rock that actually caps or holds the material within the reservoir. So you need this particular sandwich. You need a source rock, a reservoir rock, and a cap rock in order to even hope to produce any oil from the sediment, providing you have the right kind of sediment. And then, in addition, that whole package needs to be deformed to form what are called traps. I can't see my slide. to form traps, which are places where the oil will actually pool so that you could put a drill in and access it. So all of these different processes and all of this whole entire sequence of events has to occur in order for oil to form. Okay, but that's not the end of the story, because you also need sort of what I call the Goldilocks part of the story. And that is, you've got to take this package and cook it. And you've got to cook it through in the heat of the earth, but you don't want it to be too hot, because if you make it too hot, then all of the oil and gas will just go, all of the organic material will just oxidize and disappear. If you make it too cold, it's not going to form at all. So it has to be just right. In other words, the temperatures and pressures in the earth have to be within what is called the oil window. So again, there's another very specific sequence of events that needs to occur. And the other thing that you've probably figured out is that this does not happen overnight. You can't make oil in 50 years or in 10 years or in 7 years when we are probably going to be at peak oil if we aren't already there. This takes, in many cases, millions of years. This is the Ventura anticline, which contains one of the youngest known oil reservoirs, and it has a 1-million-year-old volcanic ash layer in it. So the process takes a long time. Most oil comes from rocks that are hundreds of millions of years old. So it doesn't happen overnight, which is why it is clearly a non-renewable resource, at least non-renewable in our lifetime and in the lifetime of current modern civilization. Okay, so the oil then has to form it has to collect in traps, and then people can put wells in above and tap into those traps where there are pools of oil that can be pumped out and used to produce oil. Now, one of the simplest kinds of traps, or one of the simplest geologic settings in which oil was found, was what's called a salt dome. This is a layer of salt that originally existed in the earth, and the salt is actually less dense than the surrounding rock, so the salt begins to rise up through the layers above it. And as it rises up, it deforms some of those layers, and if those layers contain the right sequence of rocks, then that produces a trap or a set of traps, and those traps can then be tapped for oil. And in fact, in the Gulf Coast, much of the early oil came from these salt domes. And finding the salt domes, in some cases, was fairly easy. You go out in the marshes of Louisiana, and because the salt is buoyant and is pushing the rock up, in some cases, like this Avery Island dome, it actually the dome itself sticks up a little bit above the swamp, and you can fly over it, identify the dome, put a drill rig on it, and drill, which is why this is one of the earliest sources of oil in the Gulf Coast. In other places, the domes are not clear from the surface. And so in order to find the domes, what people had to do is go out and do remote sensing, and the earliest methods, in many cases, were gravity. Because the dome has a lower density, there's a very slight gravity anomaly. You go out and measure the gravity very, very carefully over this area, and wherever you have a salt dome, you get this bullseye pattern of a change in the gravity, and that identifies the location of the salt dome. But not all the oil was found in salt domes, and people needed another way to look down into the earth. And the way they did that is using what's called seismic reflection, or reflection seismology. You put energy into the ground, that produces waves that go down, they bounce off of different geologic layers, and then you have a set of devices that pick up those waves. Excuse me. Devices that are typically called geophones. The original geophone arrays consisted of maybe 8 or 10 or 20 geophones. The source was originally a hammer in some cases, hitting the ground or hitting a metal plate. Then people got a little more sophisticated. They started setting off explosions to produce this. And now things have gotten much more sophisticated. There are trucks that are called thumper trucks. These are huge trucks. They have a metal plate between the front and the back wheels. The metal plate is put down in contact with the ground, and then all of that equipment above it vibrates the plate. And that puts energy into the ground, and then people put out geophone arrays, not 10 or 20, but sometimes not hundreds of thousands, but tens of thousands of geophone arrays spreading over many, many miles. So these trucks will go along, shake the ground, the geophones will pick it up, then the trucks will advance a little bit, do it all over again. These are big, complex, time-consuming surveys that require an awful lot of computer processing. But we now have that kind of capacity, and so this is done. And you can also do it at sea. There's an equivalent of a geophone that you can drag, you can mount in an array and drag behind a boat. And then you also drag something else on the boat that uses a sound source to produce that impulse of energy that then goes down and comes back up. So with all of this technology, it's possible to image what's down inside the earth. And that's now typically what's used. It's been used for many, many years to do petroleum exploration. And here is just one cross-section that was produced. And if you have some information about the area, you can start looking for structures in the ground that are likely to produce oil. If you strike oil in one place, then you can look for analogous structures nearby that might also contain oil. Can I have some water, please? This has gotten even more sophisticated, and so much of the seismic work that is done now, thank you, is done not using two-dimensional but three-dimensional seismic data. They spread out these arrays in a grid, and they use again, with the kind of computing power we now have, they can actually produce three-dimensional diagrams. You can actually project, in many cases, in some of the large companies, they project all of this into a room, and you can put on goggles and put on gloves and walk in and move around within the geologic formation, looking for the signs of the things that are likely to produce oil. So this is a very sophisticated game. It's a very sophisticated business. A lot of time and effort has gone into it. There's a lot of geologic input because you need to be able to understand what it is you are seeing when you see a diagram like this. And this is a tremendous effort that has gone into it. It's paid off. We have found a lot of oil. But as time goes on, the methods have had to become more and more sophisticated because all the easy stuff was found. And so every time it looks like they were running out, they needed to come up with more and more sophisticated methods to find what turned out to be less and less oil. Okay, the take-home message from this is that oil forms under special conditions. It takes time to form. There's only so much of it. It isn't easy to find, and most of or all of the easy oil has been found. Okay, now what happens when you find some oil, you put in, where you think you found oil, you put in a well, you drill, and you find oil? This is what the production from one single well will look like. Okay, there's some ramp-up time as you're getting it online, and then you pump at a constant rate for some period of time, and then you pump it away. You start to pump it out, and so the production tends to decrease. That's one single well. If you have an oil field and you have lots of wells, each well will have a curve that looks like the curve I showed you. And if you take a bunch of those curves and add them all up, you get the black line that you see, which is the production curve for an oil field. And you get this thing that looks kind of sort of like a bell-shaped curve, like a Gaussian curve. And the person who really first identified this, who put it all together, was M. King Hubbert, who, as we all know, is the father of the Hubbert curve. And what he said is, well, to a pretty good approximation, any oil field is going to follow more or less a bell-shaped curve. And not only that, if you take a bunch of bell-shaped curves and add them together with different heights and different time scales, what you get is more or less a bell-shaped curve. And in 1956, which is where the red line is, Hubbert took the production from the United States, U.S. total oil production, which are the black dots to the left of the red line, and he fit the blue curve to that and predicted that in 1971 we would reach peak oil production. Well, the black dots show you what happened in the United States in the subsequent 50 years. And okay, production was a little bit higher at the peak than he predicted, but more importantly, he had the general shape, he had the peak time correct, and I guess most importantly, he actually predicted the depletion of U.S. oil resources.